One thing to clarify going forward is I wanted people to do example 4.1 and turn this in. Just follow along with my video and this book and just produce the answer at the end of the book. And I wanted that as like a, just like a participation point, essentially. But if you already turned in homework 4.1, that's fine. I'll just put 4.1 as a homework, and you don't have to turn in the example. I just want people to, go through this and have points for going through this. Okay, so this is zero force. We just did that. All right, method of sections. This is really cool. Method of sections. So oftentimes you might want to know just one member in a truss. So maybe you're installing something, or maybe one is failing. Maybe you want to reinforce one member because it's rotted out. I just skipped example 4.5. Yeah, let's do this one. So say you want to replace. So they're saying in this example, determine force in members F, H, G, H, and G, I. So here's F, H, G, H, and G, I. But this could be real. Like, say you had a leaky roof for a long time, and you're losing one of your sections in your roof. You don't really want to solve through method of joints all of these things. So what you do is you, just like normal, will, one, solve for reactions. Then you can take a cut of your truss bodies and then you'll solve for those members only in order to keep that body from either translating in space or rotating in space. So in this particular example, you'll have your reactions first off, and then you can take, and instead of solving for the whole thing, hang on, I'm just talking. Gosh. So okay, let's just do like a quick note here. So like, if you were to cut your truss system and you had a reaction out here and you had a force here. Nah, this one's not complicated enough. Yeah. I think this was the Fink. Okay. So yeah, you have some sort of loading and some sort of reaction, and these all were to keep the structure static. So now, if you wanted to solve for maybe like one member, you could take a cut through that one member, and then you would have these vectors here. So those are the vectors of the members you cut. And then the rest of this body still needs to be static, even with your loading. And now you've cut it, so these are all cut, and you're missing this reaction over here. So now you're going to solve for these members as if they were the reactions, such that sum of forces in the y equals 0, sum of forces in the x is equal to 0, and sum of moments. So you're turning, all these little method of joints problems into one problem, and it's pretty cool. It's less work. So let's go do the real example here. Let's see. So this is pretty cheeky in the problem. They say because there's a symmetry to the loading and the loads are all applied at joints here, and then the reactions are also symmetric. So they're saying they have 2 kips, 2 kips, 2 kips, 2 kips, 2 kips. And it's symmetric, all equidistant by 8 feet. So they're saying because this is symmetric, the reactions are going to be. So like there's 2 vertical reactions, so those 2 reactions are going to be the sum of these. So 2, 4, 6, 8, 10, and there's 2 of them, so this is 5 and 5. And that skips the whole step 1, find your reactions. Now, say you want to identify this body here. Oh, I got off screen. Say you want to identify this force in this member, and you want to reinforce your roof there or something. So now you're going to cut through your truss system. And let's see, we've got a G here. Something like that. There's something here. You're going to cut right here. Okay. So now you have an unknown force this way, but you know the direction. An unknown force this way, but you know the direction. And this is from H. This is not cut. This one is I. And then you have an unknown force this way, but you know the direction. So this is 3 unknown forces. And where are we at? J. And then there's a vertical here. And then there are still these 2 kip loads because we're still including these joints, H and J. And then we have this 5 kip. I'm off screen. We have this 5 kip reaction still because we kept this joint L. So we have 2 kip loads, an unknown load, unknown load, unknown load. And then there are forces in these members, and we do not need them yet. We want to know what forces are on these members that keep this system static. And then you could really hone in on one member. So you're going to do sum of moments are equal to 0. Oh. And the real trick here is that you can pick anywhere you want to do a sum of moments about. So if you look closely, these vectors intersect at some point, and these are the joint that we cut off. So you could take a sum of moments, out in free space, or you could take a sum of moments where these two are intersecting, and then it will basically suspend disbelief for these two. Like they're 0 distance perpendicular away. So if you did your sum of moments about, what was this, G? Then these 2 unknown forces would not matter for that one sum of moment. because they're zero distance away. And then what is this, HF? So really we would have HF, and we would want to find how far away this HF was from G. And then, so it would be FH at that weird distance. So in order to find that, we're going to need a triangle. So I would really need to now define my geometry better. So between G and I could do this graphically. I'm missing an opportunity. Where's my paper? Oh, under here, of course. Between G I. So that's 8 squares. So that's 8 feet. And then I go 9 feet up to get from G to F. 3, 4, 5, 9. Here's F. And in this case, G and F are both cut off. So like, I'm just using them to find my direction of my vectors. And oh, weird. Okay. 4, 8. Okay, I need one more. L. Now I need a straight edge. What? So that's my directional component between H and F there. H and I have a member. This one's not cut off. This one is. This one's cut through. So our cut's right here. And I want to know this direction, and that direction. And I've got 9 feet here, 8 feet here. And each one of these is 8 feet. So then this is 9, 24. So could have 3 to 8. This is my direction. So I'm just saying for my own benefit that this direction is the same as this direction. It's like just a proportionally smaller. So I kind of want to know this length. No, this is orientation. Sorry. Right, so this is angle. Is that going to help me? I really want to know. Yeah, my distance here. So if I had a right angle, I'll have a distance vector between this vector FH and G. It's also a right angle. I know this side is 9. I could get this angle here. Cool. Yeah, so this smaller angle complements this one up there. So I'm going to go ahead and get... Well, I already know the hypotenuse, right? Oh yeah, I still need the angle. Okay, I'm going to get that angle. So... Right, yeah. Yeah, I'm just making sure that I have this right. Yeah, so this angle that forms here is also this angle here, which is over here. So that would be 3 adjacent. Cosine of the thing I want to know. Yeah, actually this triangle's not even that important, is it? Yeah, I guess so. Yeah, it is. Huh. Crazy. So inverse cosine 3/9. .53. So now I know this angle from this triangle there. Now I want to know this distance. And 9 is still my hypotenuse. Yeah. Really? Huh. It took a really long way to work that out. So it's opposite of this angle. Sine this angle times... So here's my value I want. Oh, I'm running out. Oop. This is feet. Okay. Cool. So now all that was just to take the summer moment. About G. So because I'm taking the sum of moment about G, I don't have to find the distance that this vector is from G, and the distance from that vector is from G. kind of like the other paper better now. So 2 kips here, 2 kips here. And then there was a 5 kips down here. Oops. So if I were to do a sum of moments about G, to keep the structure static, it would need to be 0. So I'm checking for rotation about G. And so I have a force here at a distance of 8.5, which is actually 8.4485 feet times whatever force exists between H and F member. Is it positive or negative? I'm not sure. I'm just going to assume it's positive, which would have put it counterclockwise. Next, we have a force of 2 kips at a distance of 8 feet, and that one's negative. 2 kips, 8 feet. Then 2 kips at 16 feet. Kips, 16 feet. Then a positive 5 kips at 24 feet. And that do all of that in my head. Divided by 8.4. Okay, I got the force of HF equals 8.48, 4.8949, and this is in kips. Cool. And so similarly, you can take your sum of moments around anywhere. So now we have the load that this one member is experiencing using statics. So now if you want maybe this member only, you would do the same thing. You would take sum of moments where these 2 members intersect, which is all the way down here. And so if you take your moment about L, this would be your only unknown in that sum of moments. Need more paper space. So sum of moments about L. Yeah. 0. So now you're going to enumerate every unknown and at what distance it is from that point. In the book, they break it up. They decompose this force GH into like a vertical component right here. And then that vertical component is, 24 away. But then you'll still need to do some trig to get back. Which is fine. It's not too bad. But otherwise, if you didn't want to break it down, you could, again, solve for like a normal direction distance. And you'd create a new triangle. So, in this case, do you have enough information to get, I mean, you're probably going to, what was the distance on this chord? I never got it. Whatever. I think to make it easier, we'll just do what the book did. So it's easier to follow along. So yeah, I like to. Okay, so I'm pivoting around L out here. Let's see if I can open this view up. So I like to start from the bottom. So let's just do GH vertical, and they called it VGH. Is at a distance of 24. So it's all the way across over here. And that's negative because it's coming clockwise. Sorry, I assumed it was up. Yeah, we'll just have to reason this one out. What else do I have on my static structure? Missing this one. So I've got 2 kips coming down. So this one's actually positive. 2 kips. Since it's down, I can go by the horizontal distance. 16. 2 kips. Another 2 at an 8 distance, feet. 2 kips. And my reaction here is vertical, but I'm about L, so this distance is 0. This FH vector that we just solved for crosses right through L, so the distance of 0. And GI vector crosses through L, so distance of 0. So this one's pretty easy. So maybe it's worth doing the vertical component. Okay, I have a calculator. I'm going to do it. Whoa, that's a big number. 16 times 2 plus, that's why. I had to put times. Okay, so this is 48 over here, divided by 24 is 2. So the vertical component is only 2. Two in magnitude. See, because I just put a negative there, I'm going to have to figure it out. What is the direction of my GH vector? So I'm pivoting about L. Let's say this is L. And really, I've got forces down and down. So to keep this from moving about L, I would really need some sort of a upward direction to resist it. So I'm going to say if these two forces were in the negative direction, this one would have to be opposite. So I'm going to say this is positive 2. So I had just kind of arbitrarily assumed up, and so that is right. Now I've got 8. So yeah, this vertical, I think, is only 6 up. And this is 8 by 6 to get to H here. This one's 8. So if my vertical component was, 2, if I had 2 there, 2 is to horizontal as 6 is to 8. So maybe I should have done the inverse. It's a ratio, I can do that. So my unknown 8. Do I know this length? It seems so easy to get. Well, I will in a second. So you can solve for H to get this horizontal component. I'm going to do square root 6 squared plus 8 squared. So this is 10 long. So now, just to bypass even more, I'm going to say 2 is to 6 as GH is to 10. Cool. So Three point three. And that's what they got. Cool. So yeah, method of joints. You can really hyper focus on one member. And I'm gonna make another video on before you start working with any truss. You really should, if you want to use method of joints or method of sections, you really should do this guy, 2j m plus r. So this is the number of joints you have. This is the number of members you have. And these are the number of reaction forces. And so these are like your unknowns, and these are like how many equations you can form. So for the one we just did, just to show you an example, move this over. So this is a lot of members, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So you could imagine if you went through all this work and then it wasn't solvable or something like that. So let me write that down before I forget. 21. I have 3 reactions basically always. And then my number of joints, it's A through L. 12. So that's 2 times 12. So 24, 24. So before you start using method of joints and method of sections, check that it's solvable. And I think that's going to be it in a big way for statics. I do really want to go over frames, but I think I'm going to make it like an extra lecture. So from here, I'm going to assign homework. So yeah, please turn in the example we just did together. I forget what it was, 4 or 5? It just has like a points for being in class kind of thing. Yeah, so do 4 or 5 on paper, take pictures of it, send it in as an assignment. And then I'm going to have homeworks. Let's do 4-1. 4-3. And then I want to do some zero force member problems. 4-14. And then I want to do some sections. 4-17. Let's see. 4-17. Find forces in FH, FA, GI. Yep. Yeah, that sounds fine. Okay. So let's make this your homework. 4-1. Refer to figure 4-1. Determine the forces in all members of the truss using method of joints. Indicate the results on a truss diagram. So, oh, and be careful of your arrow directions. So that would be like at the end answer, you would write your numbers and say whether they're compression or tension. And I would actually prefer if it was just tension or compression, but anyway. So that's, whew, let's see if I can get this, 4-3. That's 4 feet, 4 feet. It's got a middle member. This looks like the first problem we did. It's got a rolling joint, 3. Yeah, so another 3, 4, 5. Even the force is in the same direction. That's pretty nice. All right. 414. So 414 here says identify all of the zero force members. These guys are not vertical, but that won't matter. I don't think. Oh, it does matter. Okay. Yep, they did that. Make sure you really know it. So 414, identify zero force members. Yeah, like if the force was in line with one of these, well, no, that's fine. Okay. 417, this guy. This is like what we just did, use method of sections. All right. I think now I'm going to, so like now I would have a test on this, but I'm not going to do a test, I don't think. I'll have to, yeah. So just in credit for paying attention to these videos or just doing it on your own with the examples. And then homework. I could probably do a take-home test. I don't think I'm going to yet. Yeah, so then I'm going to do a bonus of these frames because I'm interested. Up to these method of joints, method of sections, that's basically where my statics career kind of ended. Not like my statics professors didn't go into this like frames here, which is I think is going to be really cool. So I want to do just like a freebie example on this. And then from here, I want to jump all the way through. I want to skip friction. You're going to cover that in physics, so we don't need to cover that twice. Chapter 6 here is three-dimensional. I'm not going to do that. 7 is about centroid of an area. You're going to like, we're just going to skip it. It's a lot of mathematics, and it's not directly applicable. Honestly, I do use this stuff, but then I just go to like a table to get the answer. Yeah, same with area moments of inertia. So both of these add up to being important for stress. And so I think we're going to start with stress now. The next assignments will be on stress. All right, thanks guys.